Welcome back, everyone. The topic for this next series of videos is acid-base equilibria. And the purpose of this video is going to be acids and bases, an introduction to acids and bases. So, kicking off with acids, some characteristics that we might already know is that acids are going to have a sour taste. They will react with limestone to produce carbon dioxide gas, and they can interact with alkali metals to form neutral substances. So we've got two different definitions that we're going to look at for both acids and bases. One is the Arrhenius definition, and the other is the Bronsted-Lowry definition. And you may also see later on a Lewis definition of acids and bases, which can also be important. But the first one we'll look at is the Arrhenius definition. So this was kind of the first one to come about, where compounds that dissolve in water will yield hydrogen ions, which are represented as H+. But now we recognize that they are technically hydronium ions, which are H3O+. But just keep in mind, depending on the equations that you'll look at, it could be written as either the H plus or H3O plus, and so we use those kind of interchangeably. Okay, now the Bronsted-Lowry definition is that an acid will donate a proton, H plus, to another compound. Okay, so Arrhenius is restricted by dissolving in water, so water must be present, but in the Bronsted-Lowry definition, it's more of a generalized definition where it's just about acids donating protons. Okay, and keep in mind that acids can be monoprotic or polyprotic. So if an acid is monoprotic, it means that it only has a single hydrogen that can be donated. Doesn't mean it's the only hydrogen present, it just means it's the only one that can be donated. And polyprotic acids are going to have multiple hydrogens that can be donated. Now bases, again, we're going to look at the Arrhenius definition as well as the Bronsted-Lowry. So the Arrhenius definition of bases is that they yield hydroxide anions in water, and so that's your OH negative. And then Bronsted-Lowry, again, the more generalized definition is that bases will accept a proton. So acids donate and bases accept. So most of our common bases are going to be alkali or alkaline earth metals attached to that hydroxide ion. So those again are going to be groups 1 and 2 metals that are attached to the hydroxide ion. And we'll see a list of your strong bases later on. So there are some compounds that may produce hydroxide ions when dissolved that are not your group 1 or group 2 metal hydroxides. And one of the most common examples is ammonia. So ammonia, remember, that is NH3, and it can accept a hydrogen and become NH4+. Okay, so ammonia is considered a weak base, and then ammonia, NH3, is considered a weak base. Ammonium, with the extra hydrogen and the positive charge, that is considered a weak acid. So again, base on the reactant side and acid on the product side. Okay, so let's look at some examples where we are asked to produce the net ionic equations for each of the following species acting as a Bronsted-Lowry acid. So remember that by definition, a Bronsted-Lowry acid is going to donate an H+. Donate that hydrogen ion. So what that means is that if it's donating it, it must have H+ as a product in the balanced chemical reaction. Okay, and if this reactant, if this acid is losing an H plus because it's donating it, that means that the product, the species that remains, must reduce in charge by 1. Okay, so we're going to reduce the charge of the remaining species by 1. Okay, so just some quick notes there. Remember that you have seen net ionic equations in General Chemistry 1, so you may need to go back and review that topic of how to create a net ionic equation. But for this first case, at least when we're dealing with the acids, we're basically going to disassociate those acids into their ions. Okay, so hydrochloric acid, when it disassociates, it's going to disassociate into an H plus. Right, so we're separating out these ions. You've got an H plus ion, and then you've got a chloride ion, the Cl negative. Okay, and again, what that means is that we are donating a hydrogen. It's being removed from our HCl, our hydrochloric acid species, and then your remaining species is that chloride ion, and it has been reduced in charge because it went from neutral in the overall compound to a negative charge as a chloride ion. Okay. So the second one is technically an organic compound. So when we look at CO2H, that is what we call a carboxylic acid. And a carboxylic acid can be written several ways. You may also see it as COOH, so COOH. But if we look at this drawn out, it's a carbon double bonded to an oxygen and then single bonded to another oxygen that has a hydrogen on it. And so it is that hydrogen that's attached to the oxygen, okay, that in that OH group, that is our acidic hydrogen. That's the hydrogen that's going to be donated. And eventually, if you move on to organic chemistry, you'll learn that the reason that it's this hydrogen that's donated is because the remaining carboxylate ion is stable, and it's stabilized through resonance, right? So that double bonded oxygen, that double bond can move between each one of those oxygens and create stability. Okay, but it is that hydrogen on the CO2H, that hydrogen on the end, that's going to be donated. And so when we look at the products, we're always going to have H plus, our hydrogen ion, when acids disassociate. And then we're going to have everything left, the remaining species, with a -1 charge, because the charge has to be reduced by 1. And remember, the overall charge on this original compound was 0, right? It's neutral. You don't see a charge written. And so it's going to reduce by 1, leaving CH3CO2 with a negative charge. And everything is aqueous. Okay, and technically this should be a double-sided arrow because we're going to learn that our carboxylic acids are what we call weak acids. Okay, and then this last example, it's also a weak acid, so we're going to have a double-sided arrow again. And remember, those double-sided arrows, they could also look like this, where we have one half arrow going in each direction. Okay, so both of those are considered to be the same. So in this last example, we're going to donate the only hydrogen that's present. That's that H in the beginning. Okay, so we've got our H plus, our hydrogen ion. And then everything remaining, and the charge has to be reduced by 1. Well, the charge in the overall original compound was already -1. So if we reduce that, it becomes SO4 2 negative, because we have to reduce that charge by 1 every time. Okay. So now we're going to look at the same examples but with bases, so base dissociation. Remember that by definition, bases are going to accept that hydrogen ion. So they're going to accept an H+, which means that if they're accepting it, that hydrogen ion needs to be a reactant. So H+ is a reactant in this case. And that means that if we're adding an H+ to our reactant species, then we need to increase the charge by 1 in our product. Okay, so for the bases, we're going to add an H+ on the reactant side. Okay, and both of these bases are considered weak bases. Again, we'll look at the list of weak and strong bases in a moment, but we're going to have a double-sided arrow for this. We're adding an H+ to the original reactant, and we're going to add that hydrogen to the nitrogen, because that nitrogen, remember, is going to have a lone pair, and that lone pair is going to attract that hydrogen that is missing electrons, and so that's where you're going to get that bond. And so we get CH3NH3, and the original species did not have a charge, and so we have to do a positive charge. We have to increase the charge by 1. And just remember that all of your charges on the reactant side must equal all of your charges on the product side. So if we have 0 charge on the first compound and we have a +1 coming from the hydrogen ion that's being added, right, that overall +1 charge on the reactant side has to equal the +1 charge on the product side as well. Okay, second example, we've got S2 negative. Again, we're going to add a hydrogen as a reactant. Okay, this is considered a weak base, so we're going to have a double-sided arrow, and that becomes, remember, we always write the hydrogens first, unless it's a carboxylic acid. That would be the one case where we write it at the end to show that it's attached to the oxygen, or any organic acids for that matter, right? Ammonium and ammonia that we talked about, that NH3, NH4+, well, in general, you can have amines, and so that's what we had listed in part A, that NH2 right there is what we call an amine. And so again, the acidic form of your amines, you're also going to have the hydrogen listed at the end of the species. But most of the time, if it's not an organic compound, that hydrogen is going to be listed first. And so we have HS for our second example. Overall, remember, the charge has to increase by 1. So if we started out at a -2, then we need to increase to a -1. And again, if we were to add up those charges, we've got -2 plus a +1. And overall, that would be a 1 negative, and that needs to equal the 1 negative on the product side. Okay, and all species are aqueous. Okay, so we're going to jump into our next topic that deals with conjugate acid-base pairs. So we've kind of already seen this, but in an acid-base reaction, the transfer of a proton from a donor to an acceptor is going to give you this acid-base conjugate pair. Right, when the acid donates the hydrogen, the species that remains is going to be called its conjugate base, and when a base accepts a proton, it's converted into its conjugate acid. And so we see an example down here where we've got this overall reaction, right? We've got water reacting with ammonia. Ammonia is going to act as the base, and so it's going to accept a proton from that water molecule. And when it does that, it's going to form its conjugate acid pair. Okay, so a base on the reactant side will always form its conjugate acid on the product side once it accepts that proton. And then vice versa, the water is acting as the acid. It's going to lose that proton, and so what remains after it loses that proton is considered your conjugate base. Okay, so let's try an example where we try to identify the acid, the base, and the conjugate acid and its conjugate base. So when we do this, we want to pick our first species on the reactant side, and we want to find out what it forms on the product side. So I notice that I've got this polyatomic ion, this PO4, and so I need to find that polyatomic ion on the product side as well, that PO4. And so I know that this is going to be a pair, right? I've got my H2PO4 negative, and it's becoming HPO4 2 negative. And I need to ask the question of what is happening to this reactant, to this H2PO4. Is it gaining or losing a proton as it forms the product HPO4 2 negative? Okay, and I can see that it's losing a hydrogen, right? Because it goes from H2 down to just a single H. And so if it's losing, right, loses an H plus, okay, then I have to ask, does that mean that it is accepting or donating, right? And it can't be accepting it because it's losing it. So it must be donating. Okay, and if you donate an H plus, you know that you must be an acid, right? So by definition, donating an H plus means that that must be our acid. So I'm going to write an A over top of it. Now, whatever is the acid on the reactant side, what it forms on the product side must be the conjugate of the opposite. So that has to be the conjugate base. And then we look at the other reactant that we have here. This is the hydroxide ion, okay? And looking at what it forms on the product side, we can see that if H2PO4 lost a hydrogen ion, then the OH negative must be gaining, right? Because it only has one hydrogen here, and now it has two on the product side. Okay, so hydroxide ion is gaining that H plus, which means it must be an acceptor. Okay, and if it's the acceptor, by definition, that makes it the base. And that's just to double check. Once you have determined that H2PO4 negative, that phosphate ion is your acid, then the other one must be your base. Okay, and your base has to form your conjugate acid. All right. So you can look at each one just to double check yourself, but once you determine what the acid is on the reactant side, you can kind of fill out everything else based on it. The acid must form its conjugate base on the product side, and then if the first reactant is an acid, that makes the other reactant have to be the base, and it must form the conjugate acid on the product side. Okay, now the next set of questions, they're not going to give us the reaction, they're just going to give us the reactant and ask what is the conjugate acid and what is the conjugate base. And so in just a moment, we're going to learn what this word amphiprotic or amphoteric means, but you do have compounds that can act as both an acid and a base. Okay, so for both of these compounds, they can act as an acid or a base. And so we're going to start off. If we're asking what is the conjugate acid, that means that you must be starting off with the base. Okay, and they're asking what is the conjugate acid to that base. Okay, now by definition, if we go back for just a second, remember that bases accept a H+, and so H+ has to be a reactant. So we're going to go back and rewrite these reactions, including basically this net ionic equation that we've already done. We're going to form these net ionic equations, and then that will help us determine what is the conjugate acid or the conjugate base. So if something's acting as a base, we must add the H+ as a reactant. So we're going to add an H+, and then when we add that hydrogen to the reactant species, we get H2SO4. Okay, and it started out with a -1 charge, and you added a positive charge, and so overall you should get a neutral compound. And so that is your conjugate acid. Okay, and then we're going to rewrite this HSO4 negative, and this time they're asking what is the conjugate base. And so we need to figure out what that conjugate base is. And that means that your original species must act as the acid. Okay, so acids are going to donate, they're going to lose a H+, a hydrogen ion, and so that H+ is going to show up on the product side. And then the remaining species is going to be anything left after we take that hydrogen off. So we're left with SO4, and remember that we have to reduce the charge by 1, right? Because on the reactant side, we have a -1 charge overall, and then on the product side, we've got a +1 coming from the hydrogen ion, and so overall, our SO4 must be a 2 negative charge. Okay? So our conjugate base is SO4 2 negative. Okay, so again, if something is acting as a base and you're forming the conjugate acid, then you're going to add a hydrogen to it and you're going to increase the charge by 1. If something is acting as an acid and you're asked to find the conjugate base, then you need to take away a hydrogen and reduce that charge by 1. Okay, so in the second example, again, it's going to act as a base because the first thing they want us to find is the conjugate acid. And so that base is going to accept a hydrogen ion, so we add an H+, and then the conjugate acid becomes PH4 with a positive charge. Again, we add a hydrogen and add a positive charge to it, or increase the charge by 1. And then vice versa, if we start off with the pH3 and treat it as an acid and ask what is the conjugate base, then we need to remove a hydrogen because the acid donates it, loses it, and so we get pH2, and we've got to reduce that charge by 1 so it becomes pH2 negative, and then you have that hydrogen ion floating separate. Okay, so a brief discussion on acid ionization. This is kind of a review from what we've seen so far. But when a Bronsted-Lowry acid reacts in water, remember an acid is going to donate a hydrogen. So the acid hydrogen will be donated to the water. And when that happens, you get that H3O+, which we've been talking about. Remember, that's what we call the hydronium ion. And these equations for acid ionization, they're going to be important when we talk about the Ka and the Kb values later on. Okay, so this is just an introduction to what the reactions look like whenever you have an acid reacting with water. And then we're going to have, of course, the opposite, which is a base reacting with water. And the base is going to accept a hydrogen from that water molecule. So again, that nitrogen with that lone pair will take the hydrogen off of the water molecule and leave you with your hydroxide base, or your hydroxide ion, which is your conjugate base. Okay, and again, these reactions are going to be important when we look at Kb values. base ionization constants later on. So we've already seen a couple amphiprotic or amphoteric. These words are kind of interchangeable, but amphoteric species are going to be capable of either donating or accepting protons, and so they can act as both an acid and a base. And water is a good example, right? In the past two examples, in the first example, we saw water acting as a base. And then in the second example, we saw water acting as an acid. Okay, so it can go either direction. And so we can have what we call autoionization. Autoionization is when you have two molecules that are the same and they're going to react with each other to form ions. And so water, if it reacts with itself and you have two molecules of water, one will donate the hydrogen, so one will act as the acid and one will act as the base, which receives that hydrogen, and so you get this mix of hydronium and hydroxide ions. And so this happens to a very small extent, and so we can form our equilibrium constant from this. Remember that we are excluding the two water molecules because both of those water molecules, are considered to be a liquid, right? And we don't include liquids in our equilibrium constant values. And so the equilibrium constant for the ionization of water, and we're going to abbreviate that as Kw, where the W just stands for water, that's going to be equal to the two products, the concentration of our hydronium ion and the concentration of our hydroxide ion. And remember that your equilibrium constants, they are based on temperature. So at 25 degrees Celsius, which is roughly room temperature, our Kw value is going to equal 1.0 times 10 to the negative 14th. Okay, so as long as that temperature doesn't change, then that Kw value is a constant. And for the purposes of this class, we're always going to assume that the temperature is 25 degrees Celsius. Okay, so our next example, we're going to use that Kw equation, that equilibrium constant, where it's equal to the hydronium ion concentration times the hydroxide ion concentration. Okay, so the hydroxide ion concentration in household ammonia is 3.2 times 10 to the negative third molarity at 25 degrees Celsius. What is the concentration of the hydronium ions in solution? And so whenever you're trying to solve for one, if you're given the other, we're simply going to take that Kw value and divide by the ion that we have, right? So if we're looking for the hydronium ions, H3O+, that is going to be equal to Kw divided by the hydroxide ion. So of course I'm just rearranging this original equation. And so we can plug in Kw is a known constant, 1.0 times 10 to the negative 14th, divided by the hydroxide ion concentration that they give us, 3.2 times 10 to the negative third molarity. And the hydronium ion concentration, that's got two significant figures, and so we want two sig figs in our answer. And remember, I'm sorry I put this unit here. It's better to just not use units in your calculation, and remember that you have to add the units for concentration at the end, right? Because our Kw value is assumed to be unitless. So the hydronium ion concentration will be equal to 3.1 times 10 to the negative 12th molarity. Okay, and so of course don't forget to add that unit back in. Okay, and I think that ends this section on our introduction to acids and bases, and then in the next video we'll talk about pH and pOH.